So I'm hoping you noticed, or are noticing, or something, that this shape is basically a trapezoid. So all I need to do is find the area of that trapezoid, and I will have effectively evaluated that integral. Because remember, the meaning of this is simply the area between the curve, which in this case is a straight line, and the x-axis, between A and B. So that allows me to draw in those links right there, which is just a trapezoid. So the formula for the area of a trapezoid is 1/2 base 1 plus base 2 times height. So let me use a different color. So this right here would be like base 1. And this little guy right there would be like base 2. This right here would be the height, and you're probably wondering, why is the height on the x-axis now? It's just kind of the way this trapezoid is on its side, I guess you could say. So that's why. So I've got base 1 plus base 2, 1/2 of base 1 plus base 2 times the height. So the way I'm going to find the height in this scenario is just to subtract the x values. And so that would be 1. And the way I'm going to find base 1 is to figure out where 1/2 hits this curve. And then the way I'm going to figure out base 2 is to figure out where 3/2 hits that curve. So base 1 is going to equal -2 times 1/2 plus 4. So that's -1 plus 4 is 3, which I can see it kind of hits right at 3. Base 2 of this trapezoid is where 3/2 hits the curve. So that's going to be -3 plus 4 is 1. And then the area would just simply be 1/2 times base 1 plus base 2 times height. So 1/2 times 1 plus 3 times 1, which is 1/2 times 4 times 1, which is 2. So this integral is equivalent to 2. And I found it by just using a formula for the area of a trapezoid using geometry. That's basically how I'm going to do 3, 4, and 5. Because they all have the same instructions. You use the graph of the integrand, which is a fancy word for the function inside, and areas, meaning known formulas, to find this integral, since we have not yet learned other ways of finding that integral. Okay, so this one here, I don't know if you've noticed how often calculus likes to use that equation. That is of the form r squared minus x squared all inside a square root. That is a half circle. So if you don't know, now you know. All right, note to self. So my radius for this half circle must be 5. And I'm going to go ahead and sketch the graph over the interval from -5 to 0. And again, it's a half circle, so it has a radius of 5. The center is at 0, 0. So I've got this graph. But the only part of that graph that I care about is from -5 to 0. So I only care about this part. Now remember, this right here simply means the area underneath that half circle and above the x-axis. So all I have to do is find that area, and I have successfully evaluated the integral. So this is basically just 1/4 of a circle. Because if I completed the rest of the circle, and I know the formula for the circle, and it's just 1/4 or 1/4 of that circle. So it basically would be 1/4 times the area of a circle, 1/4 pi r squared. We noticed earlier that the radius was 5. So the area under this curve from -5 to 0 would simply equal 1/4 pi 5 squared. So it's basically 25/4 pi, or we could say that is 6.25 Ran out of room. Right here. 6.25 pi units squared. And I'm done because I found that area. So once you've found the area, you have successfully evaluated the integral. Same idea in number 4. Nothing different. I'm going to sketch the graph from -1 to 1. So remember, whenever you see absolute value, the graph looks like a V. So, and this V is actually going to be facing down because it's negative, and it's going to start up at 1. So there's 1, there's 1, there's -1. So it starts at 1. That's what that means. And it's going to be facing down with the slope of 1. So it goes down 1, over 1, and then also to the left. And there's our graph. And that's perfect because I want to know the area between that curve, or this V, and the x-axis between -1 and 1. Well, hopefully you're noticing that's just a triangle. I know a formula for that area. That's not a problem. So I can basically evaluate this integral by finding the area of the triangle. Well, I know that areas of triangles are 1/2 base times height. So I can use this distance here between 1 and -1 as my base. So that would be 2. And I can use this perpendicular altitude or height, whatever, which is between 0 and 1 as my height of the triangle, which is basically just 1. And I can just do 1/2 base times height. So 1/2 2 times 1 is basically 1 square unit. And I have successfully evaluated the integral by finding the area under the curve using simple geometry. Okay, same idea with number 5. I'm going to sketch a graph of -20. So we just need to remember that's a horizontal line. The difference with this, however, is that it's below the x-axis. So I just need to kind of point out to you. Let me go ahead and draw the graph real quick. And I'm going to find the area between this curve and the x-axis from 3 to 7. So I'm finding this area right here. But the area is below the x-axis, so you need to make a little note to yourself that area below the x-axis is considered to be negative area. Which you're probably wondering, how the heck is that possible? This is where we sort of have to let go of our geometry and allow area to be negative. And this area is going to all be negative because it's all underneath the x-axis. Now this is great because this really is just a rectangle. So I just need to find base times height. So my base here would be 4 because it's the difference between 7 and 3. So 7 minus 3 is 4. And the height would be 20 since it's between 0 and 20. And so I multiply that together and it's below the x-axis. So that area would be considered -80. So I basically do area, which is base times height, was 4 times 20, but it's below the x-axis, so it's -80 units squared. All right, so the last video will be finishing the 3rd page of notes.